All right, Osman, I'm starting it just to let people come in, but we're not going to start until a few more minutes.
So will there be a host introducing me, things like that? Or will you be the host? Like once we start the, should I just go ahead and start by myself, or, you know, will there be someone? Oh, you are muted, Thomas. Oh, okay.
I'll start the introduction and then I'll hand it over to you.
Okay.
So I'll let you know, a few minutes. Okay, looks like we'll get started. It's just a minute past the hour. Just before we start, a couple of housekeeping ideas for everybody. We are going to have the presenter give his presentation, and then you may be able to ask questions in our Q&A or through our chat, and we will read those questions after the presentation is done. And then we could even bring, if you want to have a discussion, we can spotlight you and bring you in on it to have any verbal discussion if need be. So with that, we are going to welcome our presenter. Let me give an introduction to Dr. Osman Azbulit. He is an associate professor of civil engineering at the University of Virginia. He received his MS and PhD degrees from Texas A&M University in civil engineering. His research focuses on smart materials and technologies for resilient infrastructure, nano-reinforced and sustainable composites, and structural health monitoring. He serves as an associate editor for the Journal of Intelligent Material Systems and Structures, as well as for Frontiers in Built Environment Structural Sensing Journal. And with that, Dr. Azbulit, I will present this to you. You can go ahead, and you're already sharing your screen, and start with your presentation. Thank you.
Great. So thank you so much, Thomas, for the introduction. You see my screen, right? Like,
yes, we see your presentation. Everything looks great. Video looks great. And yep.
That's great. Yeah, thanks again for the introduction, and thank you also for the invitation to present my work at LEHIGH. So today, what I will do is basically I will go over and some of our work, experimental work on the development of passive seismic control devices using shape memory alloys. So the shape memory alloys have been investigated for civil engineering applications for a while, and there have been various studies on that, and there have been various experimental and numerical work. The experimental studies have been mostly on small-scale devices, although not completely. But also there have been extensive numerical studies illustrating the potential benefits of using the SMAs or SMA-based control devices in earthquake engineering. So today, I will not present any of our earlier work on the numerical investigations where we explore the benefits of the SMA-based devices when they are incorporated into the buildings through the numerical simulations. But instead, I will just try to present some of our work on the development of relatively larger scale SMA-based control devices. So let's start maybe with a brief introduction. The current seismic codes aims to protect the occupants and limit the damage, but they do not necessarily address the continued use and functionality of the structures. So in general, the inelastic deformations at predetermined locations provide the ductility or the energy dissipation, and this inelastic deformations later leads to the damage and the inelastic behavior, and it needs to be replaced at least if it is the case, if it is possible. If not, maybe the extensive repair is required. So these inelastic mechanisms include the beam ends in the moment resisting frames, or the plastic hinge zones at the concrete shear walls, or the braces for the steel brace frames. Another consequences of inelastic deformations in these plastic hinge zones is the accumulation of the residual deformations or the drifts in the buildings. And this residual drifts is an important performance characteristics. And if they are larger than a certain value, such as 1%, it may require the major structural alignment, which may not be economically feasible. Overall, we can say that the current seismic design philosophy achieve what it is designed for. For example, the Christchurch earthquake sequence was a kind of a big lesson for earthquake engineering community. So no structures built with the modern codes collapsed. However, extensive damage occurred in many of the buildings, which led to the demolition of these buildings and the extensive the financial losses. That illustrates that this as intended seismic performance can protect the occupants. However, it may also meant like the heavy damage that is impossible or uneconomical to repair. So why that matters for us? We, as most of know, and also highlighted in a recent study, almost half of the U.S. population reside in portions of 42 states that are at risk of experiencing a damaging earthquake within the next 50 years. So it might be a little bit tough for us to visualize the potential consequences of such an earthquake, as the latest strongest earthquake in the US, or the major earthquake that led to the significant damage, was in 1994. But there have been several scenario-based studies where these potential impacts of the future large earthquakes were investigated. Here I'm just, I will just briefly mention about one of them, this Hayward earthquake scenario. It is a hypothetical earthquake with a magnitude of 7 occurred in San Francisco Bay Area on the Hayward fault, and the findings of the study illustrated that the direct losses related to damage in buildings will be more than 82 billion. So if you look at the if we look at the buildings in the region that are affected by this hypothetical earthquake, we can see that almost half of the buildings are will not be reusable. So they are either the collapse, unsafe to occupy, or restricted for the use. So this is what we will end up and when such an earthquake happens in the Viscous. And I want to also highlight that the study conducted by USGS assumed that all these buildings are following the requirements of the modern seismic design code. So, but on the other hand, the same study also did a survey to understand what are the public perceptions on the potential performance of the buildings, and they surveyed 800 people, and as you can see, most of these people expected that the buildings will be habitable, or some of them didn't mention any opinion, but only as a small percentage mentioned that they are they are expecting only life safety performance. So overall, this indicates the need for maybe the enhanced seismic design approaches, and over the past 2 decades, there have been significant advancements as well. And this performance-based seismic design approach is one of them. And this FEMA P58 report, first published in 2012, and then a series of reports published in 2018, kind of summarize those approaches. And in performance-based design, or performance-based seismic design meets the life safety and building performance intents of the traditional code, while allowing the designing to achieve a specified performance objective. In addition to this, there has been a recent push to achieve a higher performance in the majority of the buildings. The Congress mandated the NIST to identify the research needs towards achieving rapid reoccupation and functional recovery. And the NIST published this report in 2018, and one of the research needs, the suggestion was developing low damage structural systems that experience reduced amounts of damage with no permanent system level damage, such as permanent drift. So finally, the more recent, the FEMA P29 further, emphasize the need for achieving community resilience. To achieve this community resilience, this report, FEMA P29 report, highlighted that there is a need to establish a link between the design of individual buildings or lifeline systems and the community resilience, as measured by time of recovery of function. So, this recovery-based performance objectives are discussed in this report. Before maybe we look at that, let's look at some key definitions here. So first, this reoccupancy in the report is defined as post-earthquake performance state in which a building is maintained or restored to allow safe re-entry for the purpose of providing shelter or protecting building contents. So note that here it was mentioned providing the shelter or protecting the building contents. So it is not the full recovery, which is maybe another state. The full recovery is the restoration to the pre-earthquake safety and functionality of the building. And we also have this functional recovery, which is a post-earthquake performance state in which a building is maintained or stirred to safely and adequately support the basic intended functions associated with the pre-earthquake use or occupancy of a building. So maybe here the keyword is this basic intended functions. So this basic intended functions is less than this full recovery, the functions provided by this full recovery, but more than just providing the shelter or protecting the building content. So the report suggests that using this, using this recovery-based performance objectives and the development in the performance-based earthquake engineering, the future buildings should be developed, or should be designed, for better performance objectives. And this recovery-based objectives, in terms of the reoccupancy and the functional recovery, needs to be developed. But I just want to highlight that those the performance objectives can be different for given the building. So this recovery time can vary depending on the intended use of the building. So overall, what I want to highlight is that there is this push towards the designing the future buildings to be more resilient and to be designed based on the recovery-based performance objectives. So our work is kind of aims to help this to achieve this the objectives. So we are in particular we are exploring the development of shape memory alloy-based devices, and these devices, there are a number of devices that we are currently studying. This presentation will be mainly focusing on this confined superelastic damper, which relies on a shape memory alloy bar. But I will also briefly discuss about the three other systems that we are currently developing and working on them, and they rely on SMA or shape memory alloy cables. So before we discuss any of these control devices, I want to give a brief introduction to shape memory alloys. So the SMAs, they are metallic alloys. So the most common ones are the nickel titanium alloys, but there are also some copper-based SMAs, and there are also some studies to find the iron-based SMAs. There are iron-based SMAs for certain functionality, but for earthquake engineering, as I will discuss in the next slide, we are using the superelastic SMAs. And the iron-based superelastic SMAs are still being investigated. So, but the main characteristics of the SMA is this phase transformation. So SMA has two stable phases. One is called martensite, the other is austenite. And one phase, martensite, is stable, usually at low temperatures and high stress levels. And the austenite is stable at high temperature levels and low stress levels. And so depending on the initial the temperature of the material, or depending on this characteristic temperature of the material exhibit two unique properties that I will discuss in the next slides. One of them is called the thermally induced martensitic transformations, and the other is stress-induced martensitic transformations. But both of them relies on the material to experience a phase change between these two main phases, the austenite and martensite. So the first one is this thermally induced martensitic transformations. This effect is also called shape memory effect. In that case, the material is originally in its martensite phase. And when you load the material, it kind of yields similar to the steel, but when upon the unloading, you will have again similar to steel, quite the large amount of kind of remaining strains. However, heating the material to a higher temperature will recover all this residual deformations. So you can see here in this animation when the material met with the hot water, increased temperature, it just remember its original the shape. And so this particular property relies on inducing these transformations thermally. So so it will require increasing the temperature or changing the temperature. Okay, so I don't want to discuss much about this mechanism because none of our devices relies on such characteristics. So the SMAs that we are using are superelastic. They are completely passive. There is no need to change the temperature of the material to obtain this the shape recovery. So similar to the shape memory effect, when the material is loaded, after a certain strain level, you will have a kind of nonlinear behavior. However, upon unloading, the material will just follow a different path, but still will recover all the deformations and will go back to its original length. So this is the mechanism that we rely to develop seismic control devices. One more time, there is no need to change the temperature to observe this behavior. It's completely passive, and there are two characteristics that we try to exploit in this behavior. The first one is this the energy dissipation, this hysteresis loop. The area under the stress strain curve indicates the energy dissipation. The second is the self-centering ability, the recentering ability of the material. So the SMAs originally has been considered for numerous medical applications and some mechanical applications, but starting 1990s, it was also explored for civil engineering applications. So today my talk will be on the SMA-based seismic control devices, but the SMAs have been also studied for various other applications in earthquake engineering, such as using them as reinforcement in the beam, reinforced concrete beams or columns, or as beam column connections. However, so there have been also a large number of studies where SMA-based seismic control devices are introduced, but most of these devices have been small scale, and they mostly rely on wires, SMA wires. That is the most common form or most widely available form of the SMA wires, SMA materials. So our work investigates or explore relatively larger, the capacity devices. So with that, I want to maybe just now start discussing one of these devices, which is the confined superelastic damper. Basically, this is a fuse type dissipator, and a fuse type dissipator has been already used in seismic engineering. It consists of a steel bar confined with a steel tube, and they are like mini BRBs, buckling restraint braces. And this this bar dissipates the energy under tension and compression, and for the compression the buckling is prevented using different the buckling prevention mechanisms. It can be kind of a wet type buckling restrainer where epoxy or grout filled between the tube and the bar, or it could be also a dry type the buckling prevention mechanism. But the advantages of those, the small scale, the energy dissipators are that they can be easily mounted and demounted to the structure to add, the maybe additional energy dissipation. So they have been investigated to be used in the post-tensioned rocking, the walls or the beam, the post-tensioned beam column connections. So the device that we are exploring or we develop in our lab also the work similar to this fuse type energy dissipators, but they have the two advantages. One of them is that for this confined superelastic damper, there is no need to replace the damper, or they are reusable. You can, after an earthquake, you can still use the damper, whereas the fuse type dissipators, they rely on the steel to dissipate the energy. So after the work, you need to replace them. The second, they also provide, the self-centering to the structural system. But basically, this confined superelastic damper consists of a nickel titanium SMA bar with, inside a tube which prevents the buckling. In our case, we are using a wet type of buckling restraining system. So the gap between the tube and the bar is filled with the grout. So similar to the fuse type dissipators, the CSDs can be used in various the applications to provide added damping and also some the recentering. So before we designed this damper, we first studied the behavior of the SMAs in compression. So most of the studies in the past look at the tensile behavior of the SMA bars, but in this study we look at the buckling and the post-buckling response of the SMA bars, such that we have a good understanding of this response, and we design our buckling restraint system accordingly. So we tested SMA bars with different slenderness ratios, ranging from 25 lambda equals, this is the slenderness ratio, lambda equals 25 to 115. So during the test, we recorded the full field deformations using a DIC camera, and the temperatures using an infrared camera. But I will not go into the details of this measurements. However, here you see the stress strain or kind of the load displacement behavior of the tested bars. As you can see, increasing the slenderness ratio decrease the maximum peak load level as expected. But the one thing that you may find interesting is that after the buckling occurred, or when the load is removed, this SMA bars kind of unbuckle and again come back to their the original position. So we can see that occurs even for larger deformation, for the more slender SMA bars. They buckle, but upon they buckle and exhibit maybe this extensive the lateral displacements, and then the recover all this deformations. So basically, we analyze each the bar as we look at their this centerline lateral deflections, and for using those deflections, we also compute this lateral velocity, which indicates the peak the buckling load quite well. So from each test, for each tested the specimen, we characterize the buckling loads for the different slenderness ratios of the SMA bars. So then we use the kind of the theory that is already available for the design of the BRBs to design this the mini kind of the BRB type the dampers, which we call confined superelastic damper. So here the one thing that you can that the needs maybe kind of attention is the providing a sufficient kind of a great gradually changing the diameter from fuse diameter to this end the diameter, such that we don't have any stress concentrations here. The other is this the gap between the this fuse fuse or this graduation between the the fuse length to the full length needs to be the gap between here and the material needs to be the control, so to prevent any bearing and increasing the compressive forces due to that. But other than that, the two things is checked for the design. The first one is the global buckling of the CSTs, so this should be prevented, and the second one is kind of the local buckling of the SMA bars, and these two needs to be prevented. So with that, we design the different CST devices with different slenderness ratios for the SMA bars, and for the given slenderness ratio, we also change the diameter of the SMA bar, this fuse length diameter, to explore any effect of the fuse diameter on the response. But strategically, by changing these different parameters, we evaluate the response of the CSTs. And here is the procedure to fabricate these devices. The first, you have this, the original SMA bars that are machined to the dog bone shape, and then the fuse length is an adhesive, the back Teflon is used to cover the fuse length with the bonding material, and then SMA bars set inside the restraining tube, which is also finally poured with the cement grout. So then this a total of 8 bars or 8 the CST devices were tested under increasing incrementally increasing deformation loading. So and in this slide you see the results from all the tested the specimens. You can see that the first, we have a tension compression asymmetry in all of these responses, and that is due to the tension compression asymmetry of the SMA bars. So in tension, SMAs are tended to to have a flatter phase transformation region, but in compression, this phase transformation does not occur over a constant or a stress region. So we have a steeper the slope for the phase transformation region for the compression, and the other thing that I can briefly mention here, some of this the devices have failed due to some the connection issues with the MTS frame, but maybe I will talk about this in the next slide. So before we go there, we can also look at this maximum forces in tension and compression more in a systematic way. It can be seen that especially this larger diameter, the bars, the D15. By the way, here the specimen naming, in the first letters, the D15 indicates the diameter of the fuse length, and the L 337 for example represent the fuse length. So this bars with a fuse diameter of 15 millimeter usually exhibited quite good performances, where both the tension and compression forces increase with the increasing loading amplitude, but you can realize that this compression forces increase much more than the tension. So one of the devices, this D10 L150, you can see that the compression loads are decreasing after a certain point. For this case, we observe local buckling. That is why the compressive force levels has decreased for that one. And this local buckling most probably was due to the poor grouting of the device. So if you look at the energy, the dissipation maybe over this equivalent damping ratio, we can see that the bars, especially if we can focus on this, the 15 results, the energy dissipation at the 5 to 6% loading amplitude is around between 6 to 8%. So it is. It's not that much, but it is, what you can obtain from this SMA bars. And if you look at this relative self-centering efficiency, we can see for most of these devices, and by the way, this relative self-centering efficiency is defined by this equation, and here the one indicates like a perfect self-centering, where zero, the lower numbers indicates a decrease in self-centering or recentering ability. But for most of the devices, we can see that a very good, very high self-centering is achieved. And as I mentioned, we observed 3 different types of failure modes. The first one is the SMA bar rupture at the transition region from the full section to the reduced portion. And the second and third is more the test setup related failures, which in one of them the fracture near the ends of near the ends where the SMA bars grip occur, and for the other one the specimen slip against the hydraulic wedge grips. But overall, even for this, this test setup related issues, the responses of the devices were quite promising, and as I mentioned, maybe the main issue is this tension compression asymmetry, which currently we are trying to the kind of solve this maybe using 2 CST devices in one compact device. In one compact device, such that the one of the CSTs will be in tension and the other will in compression, and overall response will be more symmetric. So the other issue was relatively low energy dissipation, and in that case we are trying to address that maybe by adding some frictional damping to the additional frictional damping to the overall system. So so this is SMA, the bar-based device, the CST, but we are also, maybe more intensively exploring the use of the SMA cables in these devices, and we did extensive work on the characterization of the SMA cables. Here I will just briefly mention about them and then just illustrate some, some of the SMA-based proposed SMA cable-based devices. So first, what are the advantages of the SMA cables? As you can see, for this SMA bars, the machining is a difficulty, and usually you get this, the failure occurred at the machine, region. So that is one of the disadvantages of the bars compared to the cables. The bars are also, usually more expensive than the cables, because the cables relies on the SMA wires, and the current the manufacturing technology is specialized for the SMA wires. So the SMA bars are maybe in civil engineering, the purposes they are being used, but there is not much demand for the SMA bar. So current manufacturing is more specialized towards the wire fabrication. So the SMA cables just rely on the wires. So that makes the cost also considerably lower compared to the bars. So it also has, the SMAs also has cost advantages. Also, they provide redundancy. If some of these cables fails, the failure will be gradual, and they can be also constructed in various forms, and based on this cable form, the response can also be, the response of the SMA cable can be also adjusted. But here, I will just show some results from a SMA cable with an 8mm diameter that we tested in our lab. So here you see the response of the SMA cables at increasing, the strain amplitudes, and in the second plot you can see the response of the SMAs, SMA cable at various, the loading frequencies. So there is a slight loading effect, like the loops get a little bit smaller with the increasing, the loading frequency, but overall the behavior is not that dependent on the loading rate. Also, the cable can, exhibit, the almost perfect, superelastic behavior upon being deformed, the more than 7% strain. So if you look at the kind of the low cycle fatigue behavior of the cable, we can see that there is a degradation in the response for the first, especially the first 10 cycle. And that's why usually when we use these cables in the devices, we first, do a kind of a training cycles, train them such that they in the future they will have, have this more stabilized response. But overall, after a certain number of cycles, the behavior stabilized. Nevertheless, again, there is a slight decrease in the hysteresis area with increasing, the loading cycle. So it is also important to, develop successful anchorage systems for, for using the SMA cables in passive control devices. Maybe due to time, I will skip that part, and I will not, discuss too much. But we look at the two mechanical anchoraging system. One relies on this kind of the spike type, the anchoring, and the other one, the use a stop end anchoring. And we did the experimental testing using both, the anchorage systems and this, stop end. Perform, the considerably better than the first anchorage system. So that's why we will be using the stop end, in our seismic control devices. And this is just showing a more ductile failure for this first anchorage system, whereas a brittle failure observed for this, the first anchorage system. So and maybe I will wrap up in 5 minutes and just briefly to talk about these three devices. Our work on these systems are still ongoing, so I will not be able to present the full details about that, but I just want to show, the one result for each cases. So this is, the one of the tests that we did in our lab on the Superelastic, the viscous damper. Basically, this dampers, relies on like a two elastomers sandwich between steel plates, and they dissipate the energy in shear, and the SMA cables are elongated when the device goes, the left or right. So that is one of the devices that we are, exploring. Another device is this SMA cable bracing system. Here, this device just, solely relies on the performance of the SMA cables, but the SMAs are arranged in this, the bracing system such that they are always under tension. So here a small prototype, the bracing was tested. And you can see that we get, the almost, the perfect recentering and very good, the behavior from the bracing system. And finally, the superelastic friction damper is another damper that we are investigating. In that case, the SMA cables are combined with the frictional devices to enlarge, to increase this energy dissipation of the SMAs. As you can see here, although we have really excellent, the recentering, the energy dissipation might be, not sufficient for certain application. And in that case, here the frictional, components are adding damping to the system. So this work is currently again ongoing with the group of Professor Jim Rickles from the LEHIGH, and we are looking at the characterizing this response of the damper. Finally, I can say that these devices that we are exploring can help the designing more seismically resilient systems, as they are contributing or achieving these three goals of seismically resilient systems. They add more reliability, they lower the consequences in the structural systems when an event happens, and more importantly, they can achieve faster recovery, as they don't need any, they are kind of damage free, you don't need to replace them, and they also provide self-centering forces which minimize the residual drifts. So I have only these last two slides where I will just briefly talk about some of the challenges. So first, we need some design guidelines for incorporating those devices into the buildings. The second, although individual dampers has been tested, there is no system level performance evaluation for such system or such devices. And also for the SMAs, we have excellent models to predict the response up to the 6% strain, but above that, usually this self-centering material models assume a linear elastic behavior for this post-hardening region, which does not capture the actual behavior of the material. Finally, the cost has been always an issue, although it is going down. Still, there's it may be an impediment in real life applications, but these SMA cables or the copper-based SMAs, iron-based SMAs can lower the cost. Another thing that we have been investigating is to see if we can have kind of some self-sensing behavior with the SMAs. So there's another potential. So these devices can also serve maybe for some sensing applications. And the one of the challenges I already mentioned is this machinability. So maybe the SMA cables in that case again has advantages over these bars. So with that, I want to acknowledge the support from the NSF for some part of this work, and I want to thank you also for your attention. And with that, if you have any question, I will be happy to respond to your questions.
All right, great. Thank you, Dr. Oswald. Can you hear me? Is everything coming through?
Yes.
Okay, good. Well, during the presentation, my microphone kicked out and something happened. So I was like, of course it happens now. I'm glad you can hear me. Again, thank you. I'm going to start with the questions in chronological order. First one that we see is the SMA return to zero strain an immediate process, or is there a significant time delay between the peak deformation and the return? I'm curious about the advantages a quick zero strain return would provide under aftershock scenarios.
Yeah, it is kind of the immediate return for the superelastic. For Chev-Momer effect, the one that requires some heating, there is a response time. Using those the material as actuator, kind of heating them and waiting this response. In that case, you need to maybe worry about the response time of the material. But for the superelastic SMAs, I think the response, whenever you unload the material, it will start to recover this deformation. So it's quite spontaneous. It doesn't require the significant time lags, things like that. So it's just kind of material behavior, inherent material behavior. It doesn't require any actuation. When the load is removed, you also observe this kind of shape recovery.
Okay, and then I guess a follow up from the same person. Have the SMA been tested for a high quality? Oh, sorry. Let me repeat that. Have the SMA been tested for high quantity cyclic loadings? Is there an ultimate limit in the high load cycle quantity that breaks the zero strain return to behavior? It appears that some of your stress plots still exhibit some minimal permanent strains, and the replaceability of the fuse design suggests that they may need to be replaced. If these assumptions are true, what are the replacement criteria?
Yeah, very good question. Yeah, very good question. Yeah, I just presented one the results about like for 100 cycles, but we did we tested SMA cables over actually about 5,000 cycles. So there is a degradation, okay, with the increasing loading cycle. But I can definitely say this, especially for this recentering, the behavior, if the where is this? If the loading cycle is lower than let's say 500 cycles, things like that, we still observe this the full, almost full the recentering. But I just want to highlight that in our case we are designing those devices to be used as seismic protection devices, and a given earthquake you will not get maybe thousands of cycles. So for the seismic engineering applications for our cases, I think this the 100 cycle response provides good enough the understanding for our the material behavior, and as I mentioned, we don't see a significant deterioration in the response, although there is as I mentioned, like a loops gets a little bit smaller and the residual derivatives increase, but these are the acceptable, especially considering in an earthquake you will have, I don't know, but maybe 30, 40 cycles. So they are reasonable.
Okay. Another question from the same person related, so I'll just stick with the theme of the SMA. I know you stated that this SMA does not need elevated temperatures to return to zero strain. However, have you considered the effects of a building fire elevating the non-stress SMA material temperature in the absence of traditional loading stress strain? Would you expect these devices to be particularly susceptible to elevated temperature, as their advantageous behavior is temperature related?
Okay. Okay, if I understood the question, I may not understood fully the question fully, but let me respond, and I believe that will really help. So I think again the point here is that the SMA, this response is not temperature dependent. So we don't need, like if we are in the room temperature, if we have this material, if earthquake happens in a given temperature, you will observe such a response. Okay, but if the outdoor temperature changes, or if the temperature is different, like for example, this test results are obtained at room temperature, but if we go to the higher temperature, let's say 40 Celsius, okay, so the behavior will be a little bit different. Like what happens, the loops shift upward, okay, but still the SMA showed exactly the same behavior, but slightly at higher stress levels. So, in that sense, there is a dependency of the response to the temperature. So you need to consider that while you are designing. So one option is that you design for the worst case, for worst case, like when I say worst case, maybe for the worst performance of the SMA, or the worst performance, the performance of the SMA that is worse for the particular temperature, and then you design your system according to that. The second, maybe if the systems are being used in indoors, or if they are enclosed, maybe the temperature change will not that significant. But overall, the short answer, you need to pay attention to the outside temperature, as outside temperature can change the behavior of the material. But do not deteriorate the behavior. It just change the behavior, change the stress levels.
You probably said it. I don't recall it. What is the temperature operating range of the SMA?
So for the nickel titanium SMAs, it is usually, let's say, negative 20 Celsius. I will say in Celsius up to the very high temperature, maybe 60, 70 Celsius. And it changes. This operating temperature can change by changing the alloying ratios of the material, the percentage of the nickel titanium, or adding another ternary the element. So it can be adjusted, but for our SMA cable, it can exhibit the behavior, let's say negative 10 Celsius up to the 50, 60 Celsius.
Okay, can you go to slide 30, please? And while you're doing that, yes, I'll read the question. Let me get to slide 30. Mm-hmm. So that on slide 30, We'll wait till you get there. Okay. It appears that with every cycle, the hysteresis loop grows larger and larger. Does it mean that the SMA bars keep becoming softer with each cycle?
Yeah, again, very good question. So with increasing, the deformation amplitude, especially in tension, especially maybe in compression, the forces are increasing, and in tension, they're also increasing. But in tension, we observe this kind of a softening behavior initially, and then it's kind of hardening, okay? That is the tension behavior. So usually, like when the phase transformation initially start, then we have kind of a plateau, a constant, almost constant stress levels. But beyond for the SMA bars beyond 6% strain, it just start the strain hardening. For the compression, that hardening behavior the kind of starts with this point, like kind of the maybe I don't have a good image, but it doesn't have a clear transition region, and just this phase transformation occurs with increasing the stress amplitude. So it's more kind of post hardening or hardening behavior for the compression.
Okay, thank you. And then if you could go to slide 32.
Mm-hmm.
It appears that the stiffness in two quadrants is different. So in seismic analysis, the load frequency would be different from the one for negative loading. Is that correct?
Yeah. As I mentioned, like it depends on how, like currently I don't think that including an asymmetric device like that really a good idea. So if, for example, if this devices will be used, maybe either you need to use like in a cross the configuration, while one of the devices in compression, the other is in tension. So you always have a one tension and compression, the behavior coming to the system, such that always in the tension and compression, we will have one tension and one compression force coming from the devices, and overall response is symmetric. So as I mentioned, that is the results that we observed from this test. We were anticipating some asymmetric behavior, but it's quite significant. I don't think that using those devices with such an asymmetric behavior alone, just one devices is a good idea. It's better to pair them and use as a pair.
Okay. And then the next two questions, the last two kind of related about the impact of harsh environments, such as radiation in a nuclear reactor building or very low temperature regions like Alaska.
Yeah. So yeah, the extreme, so actually for especially the CSDs, one of their advantages is that's a very good question and reminder for the steel, this external, the fuse type dissipator, steel dissipator, they might be susceptible to the corrosion in extreme environments. So nickel titanium, that has excellent corrosion resistance. So for the cases that require or for structures that are subjected to this extreme environments, they can benefit using such dampers. But for the temperature, for the Alaska, for very low the temperatures, I think in that case maybe you need to just change the material. Here we are using nickel titanium. These are not very good for very low temperature, like beyond -10 to -20 Celsius. So, but copper-based alloys, they have much larger operating temperature range. Okay, so copper-based alloys could be the one potential for the very cold environment.
All right, thank you. That's all the questions we have. If anybody else at the last moment has anything, please let us know. But no, great questions, great discussion going on here. Thank you so much. And then I just want to make a note that if with your permission, can we post the video of this seminar on the Design State page?
Sure, sure.
Okay, yeah, we don't post the slides on Design Safe. We do post the video though in like a week or two after this.
Sure.
So there is another question just came in. Copper-based alloys have different properties than nickel titanium. Could you highlight some of the important ones?
Yeah, that's also a very good question. So the copper-based alloys, actually, maybe this is the reason that why we are not exploring them instead using nickel titanium. So they have some advantages and disadvantages. The advantage, the main advantage is the cost. So I believe the copper-based alloys relatively cheaper, the SMAs compared to the nickel titanium SMAs. And they are commercially available. A Japanese company produce, the copper-based alloys, and maybe some other companies as well. But the main maybe disadvantage of the copper-based alloys is that they have relatively lower strength. So for the SMAs, this phase transformation stress levels for the nickel titanium SMAs is around 600 megapascal, 500, 600, 700, depending on the material. But for the copper-based alloys, it's maybe around 200, 300 megapascal. So they have relatively lower strength. This is one. The second, their hysteresis loops, the area, under this, the hysteresis curves is smaller usually compared to the nickel titanium. So they have, they maybe has slightly smaller energy dissipation. But I think both has advantages and disadvantages. They're an alternative, but I personally think that the iron-based SMAs, if they are being developed right now, the material scientists are working on them. So the superelastic SMA, iron-based SMAs can be a better option compared to the copper-based alloys.
Right. And this will be the last question. I guess it's quick. Which do you remember which Japanese company produces the copper-based SMA?
Yeah, that's again very good question. As far as Fukuwama or FTM, I think the name of the company was FTM. But if the person who asked the question send me an email, I will find the exact name and send. I gave a talk in their company as well, so I will be able to even connect you with those guys.
Okay, great. Thank you. All right, that'll conclude today. Do you have any final remarks for today? Dr. Oswald, anything else you want to mention before we?
I just thought you were asking the.
Oh, no,
I want to just thank again, for the LEHIGH for inviting me for this talk, and I want to also, thank you for the audiences for excellent questions. That was really fun, to give this talk, and thank you so much.
Okay, and thank you everyone who participated, and we will be continuing the NEARI LEHIGH series within the next couple of weeks or months. So look out for that through Design Safe. And with that, we will conclude this webinar. Thank you.